Okay, there we go. And so the theorem says that the following the following three things are equivalent. So the main point here being really that the density of the intersection of the pre-periodic points of F and G is equivalent to those sets being equal. And I should say,
remind us what pre-periodic points.
Yes, I was just going to say that. I realized I didn't type that out on this slide. So pre-periodic points is the points which have finite forward orbit under iteration of F or G. So points which don't necessarily return to themselves, but reach something which then returns to itself. So finite forward orbits. And so we're basically comparing these sets and seeing what that tells us about the endomorphisms and kind of, so I think of this as a rigidity result in the sense that if they're somewhat similar, then they're identical, is what this is saying about the sets of pre-periodic points. So a couple of quick comments on this. So this is proven first by Xinyu Yuan and Shouwu Zheng here in characteristic 0, and then my work extends that to positive characteristic. And then also, I think to help frame this is a result of Farkruden, which says that the set of pre-periodic points of just one of these by itself is always dense. So each of them individually are always dense, so we're really just looking at a question of how do they intersect with each other. And using that, it's pretty immediate then that 1 implies 2 and 3 implies 1 here is also obvious. And so really the work goes into showing that 2 implies 3 in this theorem. So here's the broad outline of how we prove this. So the first step, and actually the step that'll take the most time, is just defining heights. And this is all familiar if we're over either a number field or a function field. But for more general, for finitely generated fields in any setting, this will take some work to get heights that actually have all the properties we need to get this to work. Once we have a theory of heights, then we'll show that we not only just have sort of arbitrary heights and naive heights, but that we actually get canonical heights for this F and G. So I'll say more about what that means later, but basically heights that behave nicely under iteration of these maps F and G. And then, so using that nice property, we'll equate canonical height equal to 0 with a point being pre-periodic using a Northcott property for these heights. So that equating those is a classical thing that comes from Silverman or even earlier than that. But for these new heights, that'll take some work to show that we have the requisite Northcott property. And then finally, once we've related pre-periodic to heights, we want to connect these two heights to each other. So we'll use, we're going to actually define these heights with intersection theory and then show that that gives us a way to compare them in a robust way. Let me see if there's something in the chat. Okay, cool. So that's where we're going. So starting now with defining heights. So to give us more clarity to talk about this situation where we're really working over, I guess to preview what's coming, the first result is stated over any field. We're going to do all of the work though, assuming that we have a relative finitely generated setting. So a field which is finitely generated over some smaller field. And we'll deduce the result for any field then using the Lefschetz principle from that. So we'll find some finitely generated field over which everything is defined. So we have basically two cases we're going to work in. The first I'll call base Z. And so this is kind of the generalization of the number field case. So our base is always going to be Q here. We'll then have some transcendence degree D extension of Q. And then the base of all our models, basically thinking things like integral models, will be spec Z, will be the base of all of the extensions we're looking at, or varieties we're looking at. On the other side, the more geometric side is base k. And so in this case, our base will be just spec of this little k. K can be any field, so finite, infinite, any characteristic. And in this case, for reasons that'll become clear, we're actually going to make d plus 1 be the transcendence degree of the extension. And then to give an example of really how we need all of the pieces to specify what we're working with. So if we take the field q of t over t, you could view this in either setting. You can either view it in base z, where it would be a d equals 1 extension, or you can view it as a geometric extension with d equals 0, where in both cases, the base field would be q, but the base scheme would be either spec z or spec q, depending on the situation. And these will produce different heights, kind of give us different arithmetic. And I'll show later that we can relate them, and there'll be reasons to prefer one over the other. So let's start with kind of what we have to work with for a theory of heights for these larger fields. So in base Z, the existing theory mostly comes from, at least initially, from Moriwaki. So he has, I think from 2000, a paper that is called something like, I can't remember the exact title, but heights over, or arithmetic over finitely generated fields. So in the base Z setting, so always characteristic 0 and always base field of Q. In base K, this is actually more classical. So I think most people are familiar with the examples from transcendence degree 1, but this is in Lang and Sayre's books and some others for higher transcendence degree as well, doing this purely geometrically. In either of these cases, though, there's some additional structure that's needed to actually make this work so that we can define heights in these settings. So in both cases, what you need is basically two things which together we'll call polarization. So the first is a model for the field big K. So this is a variety whose function field is big K, and it'll be a variety over whichever base is appropriate. So either over spec K or over spec Z. And then the second thing, so this B, maybe to compare to the transcendence degree 1 case that people are probably familiar with, the places, so the absolute values, which we use to define the height, just correspond to closed points of that field B. In higher, when B is not a curve, but a higher dimensional thing, we're going to be looking at closed subschemes of that as well, instead. And so we'll have that geometric structure. We additionally, though, for higher dimension, need also this set of line bundles. So these will be either in the base K case will just be regular old line bundles. On that model, there'll be Hermitian metrized line bundles in the spec Z case, since the base is not projective. And what these add essentially is a way to not just have a set of places, but a way to agree on a normalization of those places so that we get a collection of absolute values which have a product formula, so that we can make sense of heights on projective space. So that's kind of the additional structure that comes with these settings so that we can actually define heights. The fallback of this is that we require this choice. So for the geometric case, the base K case, if we have a transcendence degree 1 extension, or if we just have a number field, this can be done in a unique way. Your model is either the unique curve with that function field, or is just spec Z, or spec of the number field, with the ring of integers of the number field. But in higher dimension, higher transcendence degree, that's no longer unique. And we run into, that's kind of a serious problem for basically two reasons. So one is worrying about picking models with nice properties, if we want to worry about smoothness or good and bad reduction, things like that. But maybe more so than that is also the fact that what our goal is to compare two different heights. And if these two heights are defined on two different models, we don't immediately have any geometric way to compare them. So that's going to be a problem. So we want to find a way so that we can compare any heights directly and kind of get around this need to fix a polarization to start. So that's where we're going next. So we're going to, so suppose we have a projective variety over this, this big field K. So first we're going to define an open arithmetic model of this. So it'll be a quasi-projective integral scheme over the base, whose base change to the big field is the original variety. So these are, think of like open subsets of projective models for this, or open subsets of integral models. And the important thing is these have nice compatibility. So if you take two of these open models, you intersect them and you get a third one which embeds into both of them. And that'll be kind of how we move between these. We'll have an inverse system of these open models. Now, if we fix an open model, we can look at all of the projective varieties which it embeds into. So if we have an open model, this W, we can take a projective model, which will just be a variety into which it embeds, which is projective, and such that the complement is the support of an effective Cartier divisor. So these form an inverse system in a different way, where instead of embeddings, the maps will be dominant morphisms. But again, we have a way to make this compatible. So if we have, I guess going kind of beyond my simplistic tech diagrams here, really the important thing to say is that we have two different projective models for an open model, we can move to a third model which dominates both of them. And so the idea there will be if we have, say, line bundles on each of these models, we pull them back to this dominating model, and we'll be able to compare line bundles from two different models directly on that third one, which dominates both of them. So this is all kind of setting the scene for how we're going to relate these different models. And so now we're actually going to do that. So define a limit over this inverse system of projective models, where our limit is going to take the Picard group of the model. So actually, this should be really the actual Picard group in the base K case. It should be the metrized Picard group. So Hermitian metrized line bundles in the base Z case. So whichever one is appropriate for the case. We take the limit over this inverse system, and then just a small detail here, I'm really taking Q linearized line bundles. So take your normal Picard group, which is a Z module, and tensor with Q, so we get our Q linearized group. So this becomes a Q vector space. And then this is a direct limit since we're taking the Picard groups of this inverse system. And then here, kind of sweeping a decent bit of extra work under the rug, we can complete this so that basically we're completing with respect to the idea that we want to, if we have, say, a sequence of line bundles on different models, we want them to agree on an open set, and then we want their difference on the complement of that open set to be going to 0. So if that's the case, we're going to consider that a Cauchy sequence, and then we complete with respect to that definition. The big advantage here is that having completed this, we can now actually think about not just line bundles on individual models and comparing them, but we can actually take limits of line bundles over a whole system of models, which is, when we get to defining canonical heights, exactly what we're going to need to do there. And then finally, so this, up to this point, was all for a fixed open model, but we don't want to be stuck with just one open model. So we take a limit now over this whole system of basically the inverse system from the previous slide of open models. And here we're being a little bit more careful, where we're taking kind of compatible maps of open models. So think of this U to V being a model for X, for the structure morphism of X over big K. And so we're basically considering now limits over first all open models, and then for each of those, a limit over all projective models, which have that open set inside them. So this whole thing kind of gives us a way to compare these models coming from any different choice of model and compare the Picard groups. And then just lastly, notationally, an important case will be where this variety X is actually just spec K itself. And just to shorthand that, we'll call that just pic of K. And I'll note here, we really, in what's to come, I haven't notated it here to kind of avoid further technical details. We're actually going to work with a slightly smaller, well, actually slightly in some meaningless sense, but a smaller subgroup of this where the limits will behave a little bit nicer. So we want to be a little bit careful with which ones inside this we're working with. That'll be called the integrable line bundles. But I'll just ignore that technical detail here. So now we have these kind of extended groups of line bundles, or limits of line bundles, and we want to now get an intersection pairing on these, or an intersection product on these. So we're going to define this in a relative sense. So first, to start, let X to Y just be any morphism of projective K varieties. And we want to insist on having pure dimension n so that all the fibers behave nicely. So what we want to define here is a product as follows. So we're going to think of this as looking like an arithmetic intersection. So we're taking, this has pure, I should say pure relative dimension n here. So this has pure relative dimension n, but we're taking a pairing or a product of n plus 1 of these, and our result is something in this limit pic hat of y. And so the way we're defining this is it's essentially given to us from the Deligne pairing if we fix models for x and y. So on one particular projective model for x, mapping down to one particular projective model for y, this is the Deligne pairing, which is really just a relative intersection pairing. So you kind of define that axiomatically, taking what you want an intersection pairing over a field to look like and sort of apply those axioms to now a relative setting. If you want to know more details on that, actually, Xiao Wu has a great write-up that goes through many of the aspects of that. And so here, so basically we start with that. The Deligne pairing does this if we fix a model, and then the next step is to show that if we now take a limit of that intersection product over the limits over a sequence of line bundles, that limit converges. So that's where that technical condition I'm ignoring comes in. But we show that as long as we do apply that technical condition, we do get a convergent intersection vector here. So taking not intersection numbers, but values in this Picard group. And then the most useful case of this that we're going to see come up is when this lower variety is just spec K. And so we'll be taking then our intersection values will be in pic hat of K, which is an infinite dimensional Q vector space. So this is what I'll mean by vector valued intersections, and then coming after this vector valued heights. So along with this though, we can get R valued intersections and then heights coming up too. And so this is happening on actually pic hat of K. So the idea there is think of this as being just the classical intersection product on a model for K. So fix some, so the transcendence degree of K over little k is d plus 1, or in the base z case, it's just d. And so fix a model there and do, depending on base k or base z, either your classical intersections over projective variety over a field, or your Arikhelov arithmetic intersections. And in either case, we have an existing intersection theory that gives us just R-valued intersection numbers. And then again, like for the Deligne pairing, then what we're just, the part we need to prove is that the limits converge when we take a limit of line bundles in this pick hat here for K. So as we vary the model, we still get something convergent. So we prove that, it works out. And so we have these two different intersection products. And the value in having both of them is that we can combine them to get an R-value product. So if we take this intersection up here, we take n+1 line bundles on X, we intersect them, we get what's called an adelic line bundle in pick hat of Y. We then take a polarization, which is going to be D more adelic line bundles now on K, and we intersect the result from up here with the polarization, and we get something valued in R. So combining these will take us from vector valued now down to R valued using a polarization. So this is how we'll relate kind of this side which doesn't need a polarization to now picking one so that we get an R valued thing. So now we can define the height, which will just be a particular intersection. So to do so, we're going to fix an adelic line bundle in pick hat of X. And then we're going to take the height, not just of points, but of closed subvarieties. So if Z is a closed subvariety of X, we're going to define the height to be the intersection of L restricted to Z to the top dimension there, and then divided by, so here, L is just, think of this as being the generic fiber of L. So this is really a complicated sequence of line bundles on models. But the point of this compatibility when we did these limits was all of these models at least agreed on some open set. And so they all have the same generic fiber. And so even though this is a complicated sequence, we can unambiguously talk about a literal line bundle just on X, which is the generic fiber of it. So that's what this is. This is just your classical line bundle, classical intersections. And so this is just a number down here. This is a vector in pick hat of X. So the result is a vector in pick hat of X. And then the special case is when this is a zero-dimensional closed subvariety, then this bottom one, this sort of zeroth intersection number is just going to be the degree. And this will be the first intersection number, so it's just the push forward down to K. So this will be what are called our vector valued, with the vector space being this infinite dimensional Q vector space, pick hat of K, our vector valued heights and intersections. And so using what I said on the previous slide, using that kind of combination of our vector valued pairing and our R valued pairing, we can now relate this vector valued height to the R valued heights that existed previously. So the D equals 0 case is basically the known, more familiar existing case. So we still get really a vector valued height in the D equals 0 case, but what is K if D equals 0? Well, K is either a number field or is a transcendence degree 1 function field. In either case, we have our model is either spec Z or I guess would be spec of the ring of integers of the number field, or is the unique projective curve with that function field. And so we get a line bundle over that, say in the base K case, just a line bundle over a curve is what we get here. And you just take its degree and you get the usual R valued height. So that's kind of the known, more familiar case where we didn't really need to pick a polarization because everything was unique already. When D is larger, we pick a polarization and then we take our vector valued intersection here, we intersect with that polarization, and it produces either the Morawaki height in base Z or the geometric height in base K. And so really all this is doing, this kind of idea of vector valued heights, we're essentially just postponing the choice of polarization. So our height in here, you can think of this vector space as being representing all possible choices of polarization, and then kind of just filling in what you would get for the R valued height were you to pick each of those polarizations. So I think in some sense, and kind of how much of the proofs for this work as well, that's really what's happening is you're thinking in your mind, I have an R valued height if I pick a polarization. I just don't have to settle on one yet. We can kind of keep that choice open until later. So that has basically wrapped up the premise of defining heights and intersections for these larger fields. So now we're going to get into actually making use of them to start working back towards this question of dynamics. So we're going to want canonical heights, and then we're going to want a Northcott property for these heights. So first, what is a canonical height? So remember, we have a polarized dynamical system. So we have an endomorphism F, and then a polarization is an ample line bundle L, some rational number Q greater than 1. And we're saying that the pullback of L under this endomorphism is the Qth tensor power of L. And I'm writing this here, I'm usually going to use additive notation to keep these things simpler for line bundles. What that means is the Qth tensor power of L. So we have that structure, and then a canonical height is going to be a height which basically when you iterate F on the points, the height just scales. So the canonical height of F of X is just this Q times the height of X itself. And so if you iterate this a bunch of times, you just get, if you iterate it N times, you get Q to the N times the height of the original point. And so what's immediately clear from that then is that if you have, let's see, if you have a pre-periodic point, it will always have height 0 because its forward orbit is finite. And so it, somewhere in its forward orbit, some positive iterate further returns to itself. And so that point would have to have simultaneously height something and Q to the N times that something. So it has to be height 0. The other way around though will be more complicated to show that if you're height 0, you're pre-periodic, and won't always be true. And so what we're going to do to get canonical heights is, well, we really want, in a sense, canonical line bundles, because we just needed a line bundle, a Delic line bundle in pick out of X to define a height. And so we want some L, which basically has this same iteration property under pullback by F. And so we're going to set L bar of F to be, this is really, this limit here is, hopefully looks familiar because it's exactly the same limit that's used to define the Néron-Tate height. So you take some arbitrary height and then you kind of run it through this limiting process. Provided that converges, then you immediately get this property that we want up here.
So you forgot n, right? Right hand side with no n there.
Oh yes, you're right. I'm missing it. This should be a 1 over Q to the n. Oh yeah, I did. There's no n at all in here. So I should be pulling back consecutive iterates of this F here, and then dividing by powers of Q. Yes, thank you for that correction. So yeah, something should actually be happening in this limit. So we do that, we basically just keep pulling this back and keep dividing by this power, so that we basically force it to have this scaling property. Now it's non-trivial to show that this converges, but it does work out. And this basically to have a space in which this does converge is why we needed to complete this limit of Picard groups. Because the issue here is each of these L's here, may live on different models. And so as we're taking this limit, it's now a limit over varying models. We need to make sure that there's some way to make sense of that. So that's kind of why, or one of the reasons we had to go to this effort of taking these limits and completing them for these Picard groups. But once we have this canonical line bundle, then the height, we just define using that immediately. And it basically immediately has the property we want up here, that it does actually produce a canonical height. So now I'm going to, for the next, I think, 2 slides, specifically talk about the base K setting. Because before we get to the Northcott principle, for function fields, the Northcott principle is just not always true. And so we need to discuss some issues that come up there to make sure we can actually state something like a Northcott property. So for now, for the next couple of slides, assume we're just in the base K setting. So we'll start with a result of Baker. So this is for curves. So written here for just maps P1 to P1. So this f is just some rational function over K. And then the set of canonical height 0 points is finite if and only if either the base field little k is finite or f is not isotrivial. And so the finite case is kind of well known and well understood. It's basically just a statement that there are finitely many polynomials of bounded degree when the coefficients come from a finite field. But if k is infinite, then things can go wrong. So if we take, say, the naive height over P1 of some function field over an infinite base, everything in the little k field has absolute value 1, using just the kind of naive set of absolute values. And so the naive height then would be trivial on the whole base field. And if the base field is infinite, then obviously the Northcott property doesn't hold. And so what this is saying is basically we need to be careful to avoid that. So we need to, number 1, we have to be using the canonical height here. And number 2, it has to be the canonical height for something non-trivial for us to actually get Northcott. And I'll note here as well, so the Northcott property typically for number fields or over finite fields is not actually just a statement about height 0, it's a statement about bounded height. In the function field case over an infinite base, we're never going to get that because the problem is, even when we're working with the canonical height, this is just a kind of general property for Bay heights, the canonical height is just going to be a constant multiple and O of 1 away from any other height, or at least any other height coming from an ample line bundle, in particular the naive height. And so when we switch, say, from the naive height to the canonical height, we've sort of moved all of the elements which had height 0, which came from the base field, to now they've sort of been moved somewhere else in this O of 1 range in that error for this, but they're still out there. So once we exceed some bound, basically the bound that O of 1 relating the 2 heights is, then there are infinitely many points of bounded height again, as long as that bound is big enough. There's some conjectural things about sort of small enough bounds, but I'm not going to go into that too much here. But suffice to say, it will be strictly false in any setting to hope for a finiteness statement about any set of bounded height in the function field setting. So that was for curves, this result of Baker. In higher dimension, if we're working on an abelian variety, we can say some things a little bit more specific, but we need what's called the trace, Chow's K over K trace. And what this is, you can essentially think of this as being the largest subgroup of an abelian variety, which is defined over the smaller field, defined over the constant field. In characteristic 0, that's literally true. In positive characteristic, there's a little hiccup with that, which is that this trace map here, so this is basically embedding the trace into the abelian variety. this may actually have a finite kernel. So there are some issues that come up, and I'll say a little bit more about that on the next slide. But you can kind of think of it as being roughly a subgroup of A. And so then the Lang-Néron theorem basically answers this isotriviality question for abelian varieties. So we take the Néron-Tate height, which is just the canonical height for the endomorphism scalar multiplication by 2 on the abelian variety. And then the statement of Lang-Néron is that the Néron-Tate height of a point is 0, either if X is torsion or if X is in the trace subgroup. And so basically this trace subgroup is kind of the largest isotrivial part. And so we're saying roughly outside of the torsion things, height 0 is, or rather having, how do I want to say it? The question of how many points have height 0 is a question of just how big is the trace. So if the trace is trivial, then we get Northcott. If the trace is infinite, then we basically have to mod out by the trace to get a Northcott statement. So this covered basically 2 cases. We had curves, or at least P1, and then we had abelian varieties. But I want to be able to talk about things for kind of more general varieties in higher dimension. So we're going to need some additional terminology, which most actually comes from model theory. Let's see. So a constructible map is, I'll define as being a composition of both rational maps and inverses of totally inseparable rational maps. So things are going to be a little bit worse than kind of birational. And then we'll say a dynamical system is constructibly isotrivial, provided that there's a different dynamical system which is defined over the smaller field, which is isomorphic to this one, but not isomorphic using morphisms, and not even birationally isomorphic, but constructibly isomorphic, which is even slightly weaker because of these inverses of totally inseparable rational maps. So in the positive characteristic case, this is kind of even a little bit different, or even a little bit more general.
I don't really quite understand. So when you say inverse, it means after some Frobenius?
Yes, essentially.
Right, so both sides in the equivalent after, I don't know, I mean, there's some chain, right, of E both way.
Yes. So maybe the example I have below might help kind of clarify that a little bit. And so then the notion that I'm going to use is what I call totally non-isotrivial, which is that this dynamical system itself is not isotrivial, and it also does not have a positive dimensional periodic closed subvariety, which is constructively isotrivial. So basically it nor any eventually fixed subvariety of this like subdynamical system is constructively isotrivial. So briefly, maybe to help clarify that question, an example of why in positive characteristic we really do need this weaker statement than birational isomorphism is the following. So take a super singular elliptic curve over the base field, and then take a group scheme, which is an order P subgroup of the product of the P torsion. So that's not going to be defined over little k. It'll be defined over some larger field. And so we base change E up to the larger field and take this quotient. This is going to be constructively isotrivial, but it's not actually isotrivial because this gamma here is not defined over the constant field. And so what's happening for this is the trace of this would actually be E cross E, but we have this finite quotient when we take the trace map and embed the trace of this abelian variety into the abelian variety itself. So this is this issue that comes up. So it is it is kind of a real thing we have to worry about in characteristic P. This doesn't happen in characteristic 0. And makes this sort of, unfortunately, simultaneously, I think from these examples from the case of abelian varieties and from the Langnaron theorem, it's kind of clear that this really is the right notion of isotriviality to use here. It's also unfortunate that it's a very difficult notion to work with for isotriviality, because it's really very general and not so clear to tell if something, at least to me, this is something I want to understand better, how to tell if something is constructively isotrivial or not in positive characteristic. So now we can get towards actually making a Northcott statement for these. So first we're going to, so we're working with heights valued in this vector space. So we're really going to use, rather than being actually literally 0 in the vector space, we're going to use 0 to mean numerically trivial. So I'll use this 3 bars equivalent or equal sign for that. And the reason we want that is we want basically it to give height 0 with any choice of a polarization. So we pick up polarization, we produce an R-valued height, and we know that all of those will be 0. Is really the notion we need. We don't need literally 0 in the vector space. And so now the base Z setting. So this is proven by Shini and Shou. So here, since we don't have this issue of isotriviality and this trace, we can actually say a statement about bounded height. So we pick some line bundle to define our height. Oops, this should be just the height. So here we don't need the canonical height as well. This should be just the H L bar height. So we pick some ample line bundle, and we pick, so this is just some vector. Think of this as being our kind of vector bound on this. And this relation here, I think I may have skipped saying this earlier. So these are both vectors. This relation is to mean that their difference is sort of through this limiting process is an effective line bundle. So we're comparing things based on effectivity of line bundles here. So as long as we have bounded height, then this set is finite. So this is kind of your standard Northcott property, just with vector valued things instead. And then, so my contribution to this, and then this is also, I'll state the theorem and then say which part is due to whom afterwards. So in the function field setting, we're only ever going to hope to have a statement about number 1, canonical heights, and number 2, about height 0. So this is really kind of the best we can get. And then we'll say either if the base is finite, in which case we don't need any further assumptions. If it's not finite, though, we need to further assume that the dynamical system is totally non-isotrivial. So if one of those 2 holds, then the points of height 0, that's a finite set. And so for general function fields in any characteristic, this is my result. And last year, this was proven for characteristic 0, but again, any transcendence degree relative extension of function fields by Gautier Vigny. And theirs actually uses an entirely different method, doing everything in kind of complex dynamics there. Versus this more like algebraic geometry method that I'm doing. So in any case, though, for base Z and for base K, we have a Northcott property which at least holds for height 0 points under canonical heights, which will be good enough to make the statements we want about pre-periodic points.
I came up as on the previous slide. I do not quite understand the difference between these 2 theorems. What's the relation between them?
So the relation is the setting. So this one is when your base field is Q, and you're doing everything with arithmetic base. So everything is, all of these models are over spec Z. This is when we have a base spec K, and so everything is kind of the geometric side of things.
So, but the second one looks like a weaker than first one because of
Yeah, so it is weaker. So this first statement, if we tried to make this first statement for function fields in general, it would be false. And it's exactly for this isotriviality reason, that without some stronger statement about isotriviality, or not rather non-isotriviality, then you very well might get infinitely many points, say, that all live over the constant field, which have height 0.
but your definition of set it's smaller than before. I mean, the above you say hfx less equal than alpha. Here is equal 0, right?
Right. So this is the other difference, and this is also necessary, that we couldn't make this a statement of bounded height, at least not for a general bound. And it's basically because even when you have the canonical height, it's essentially within O of 1. So let's just so things are easier, can consider R-valued heights. So the canonical height is still within O of 1 of some multiple of the naive height. And so you are, at least if the base field is infinite, the naive height is going to have infinitely many points of height 0. And so once you exceed whatever constant gives you that O of 1 as you're bound on the height, then you will get those infinitely many points showing up again. Conjecturally, you could say that there is some non-zero, say like ample bound like this, that you could put here for this to be true. And I think that is true. I don't have a proof of that. But it's certainly not true for every bound here like this one is. But yeah, that's a good question. And they are different in kind of subtle ways. So how do we prove this? So the base Z case is proven by Shou Wu and Shenyi, and really, at least for this Northcott result, really mostly using a result of Moriwaki. So this is for Moriwaki's R-valued heights. So essentially what you do is you pick a polarization, and then once you fix that polarization, Moriwaki's Northcott theorem from his heights gives you this finiteness. And then the step is to kind of then move to saying, well, now we vary that polarization, is the height kind of approximated uniformly as that height varies? And the answer is yes. And so you get this Northcott principle pretty immediately from that. The base K case, we start kind of the same idea. So we fix a polarization. This gives us a geometric R-valued height. This is just known classically if the base is finite. I should actually, back to Shou Wu's question, this statement here, so we can actually make the full bounded height statement in the case that the base field is finite. Then we can make the same statement in both base K and base C. It's only when the base is not finite and we're instead relying on this non-isotriviality that we really have to restrict to canonical height and height 0. So for base K, for the proof, so when we're not in finite base, we use where this this idea of constructible isotriviality came from, which is a result of Chatsadake-Hirshashki, which says basically in their terminology, they said that a limited set is dense. So a limited set, really the important takeaway here is that a set of bounded height or a set of height 0 is a limited set. And what they say is that that implies that, so if you have a dense limited set, your dynamical system must be constructibly isotrivial. So that just gives us something about the original thing, and then we basically induct on dimensions. So if the whole thing is not constructibly isotrivial, we say, well, maybe there's a fixed subvariety on which you have a limited set which is dense in that subvariety. And then you kind of step on down from there, and you eventually get the result. But this induction step is why we needed totally isotrivial. So totally, rather non-isotrivial. So any isotriviality on even some subvariety would be a problem. And then lastly, like up here, we show that this is approximated uniformly as we now vary the polarization. So in short, that's how that works. And I just want to comment briefly on comparing these heights because we could pick kind of different settings here. So if we picked a tower of fields, we could have a height relative to kind of all the way down or a height only partially down. And these give us, so my earlier notation kind of doesn't take this into effect. So I'm going to kind of clarify these by putting big K over little k or big K over K1. And so basically what these kind of give us options here, that if we pick this first height, we're caring about non-isotriviality all the way over the smallest field. Whereas if we pick this other one, we're only caring about non-isotriviality, isotriviality over this intermediate field. And we have a nice way to relate them, basically using fibers of models of these different fields. So we take kind of the relative Picard group or metrized Picard group for the two, we pull it back to the Picard group of K, and intersecting with those things will get us from one height to the other. Really the takeaway from this is that we can kind of work in whatever relative situation is convenient. So I think a useful example is we have a variety over C of T. If we know that that's totally non-isotrivial over C, then we can just use the standard geometric height. So this is just transcendence degree 1. This is kind of nice and concrete to work with. We don't even need these limits of models because there's just a unique model P1 in this case. And so that's super nice if we have totally non-isotrivial, we can just do that. If not, we can still do this, but what we're going to have to do is find some finitely generated subfield of C or of C of T over which all of this is defined, and then do these finitely generated field heights over some potentially really big transcendence degree field. So the results still work, but if you have to kind of do more with these heights and really dig in and analyze them, this is going to be pretty nasty to work with. And so if we have some non-isotriviality result, then we can avoid that. We can just kind of work with a larger field where things are easier. So we have these results, and if we're not sure, we have a way to compare between different relative settings. And now finally, to wrap up, how do we actually use all of these results to compare these two heights? So we have now Northcott properties for both of our canonical heights. We just want to compare them. And so I'll just state the theorem. This is the Hodge index theorem. So the classical version of the Hodge index theorem is basically giving you the signature of the intersection pairing on a projective surface. And this is the kind of arithmetic and higher dimensional version of that. And in characteristic 0, this is due to Xinyi and Shou Wu, and then extended to positive characteristic by my work. And so what it says is basically the following. So this is kind of the signature part of it. So we're saying that as long as this condition holds, so these are the underlying line bundles. So we'll basically get a +1 signature if this were false. If everything were just pairings of ample line bundles, we're going to get a positive intersection. And we're basically saying in every other case, this square paired with the rest of them gives you something non-positive. So this is kind of a bunch of -1s in the signature of our intersection product. And then the really more difficult part of this result and more valuable part is the non-triviality part. So we want to say that this is, so again, this triple equal sign means numerically trivial. And we're saying that that is not quite the same as M itself being numerically trivial, but it gives pretty strict limits on M. So M either just comes from the base. So rather than being a line bundle on X, it's really just a pullback of a line bundle, right? An adelic line bundle on K. And then we also have this trace component here, which is basically saying things that are defined over line bundles which come from the base field are going to have trivial intersection theory as well. So these two, fairly immediate to show that this statement, that those are all going to pair with themselves to 0. And then the content of this statement is to say that those are the only things with trivial intersection. And so this is our theorem. Let me go through this very briefly. The proof idea goes back to Falting's and Grilljack at the same time. This is Falting's Calculus on Arithmetic Surfaces paper. And the main result there is on a curve. So on a curve, none of these L's show up. It's just a statement about the self-intersection of M. Then on a curve, we just relate this to the negative of the Néron-Tate height pairing on the Jacobian. So this M is just a line bundle on this curve. And so it's a point on the Jacobian. We can take the Néron-Tate height there. And we show that we get this negative sign here. And so that gives us the non-positivity of the intersection for the first statement. And we also know when the Néron-Tate height is trivial. So it gives us the non-triviality statement as well. And then sort of sweeping over a lot of sort of slightly more difficult details there, we kind of induct on dimension to get the full statement. And then, so wrapping up the result using that, so like I said earlier, we move from arbitrary field to a finitely generated field using the Lefschetz principle. So this variety X, it's two endomorphisms and their polarizations. We can find some maybe very big, but finite transcendence degree extension, either of Q or of FQ. So either, so in both cases falling over where we don't need to worry about isotriviality, we have Northcott immediately. And so we move to that setting, and then the Northcott result tells us that the canonical height 0 points are all pre-periodic, because the entire forward orbit of a point with height 0 also has height 0. There are only finitely many of those, and so the forward orbit is finite. And so we've related pre-periodic to height 0. So now we're just comparing height 0 points under the canonical heights. And what we do lastly, it's really this step 2, which is the last step that requires a fair bit of work. And so what this is saying is, well, we take the canonical height for F and the canonical height for G. We sum those line bundles to get a new height, which is going to be 0 everywhere that both of these, on points that are pre-periodic under both F and G. Well, and then we show if that set is dense, we have, so what that means is we have a dense set of height 0 points. We show that that means that the height of the entire variety is also 0. So that step takes some work there. That takes some proving. But once we have that, then this is just a statement about the self-intersection of this line bundle LF plus MG on X, and basically some top intersection power of that. That's trivial. And this L and this M are both ample. And so that being trivial is a pretty strong statement. So we apply the Hodge index theorem to that. We get that their difference is also trivial, which means that these define the same height. And so that's basically how we wrap these up. We apply the Hodge index theorem to this difference. We show that it falls into the case of that being trivial, which means that these two line bundles define the same height. And the height 0 points are what are equivalent to the pre-periodic points. And so the sets of pre-periodic points have to be equal. So that's how we wrap up the result. And I think I'm pretty close to overtime. Anyways, I think I'll stop there. And
Alex, I have one question.
Yeah.
So before you assume this F and G are polarized by same ample line bundle.
I don't believe I need to.
But when you do Hodge index theorem, you say LF minus MG, you say the same line bundle, different same heights?
No. So I'm also kind of ignoring some details here. So there's really a couple steps to get. So we don't need the same line bundle for the polarization here. So we really take LF, and then we make some intermediate line bundle LG. And so show that we get sort of a G canonical lift of L.
Okay.
And then we compare that to an MF, and then compare that to MG.
Okay.
Some intermediate step to connect these that I'm kind of glossing over. But yeah, we don't need these polars. These two endomorphisms can have really nothing to do with each other. Well, sort of a priori, in fact, if their pre-periodic points are the same, then I think, I can't remember exactly what this statement is, but I think Tom Tucker has some work showing that if the pre-periodic points agree, then we can say something about the semi-group of generated by F and G. So there's some stuff there, but I'm not exactly sure what this statement is. But yeah, I will finish there. These are, I guess, just some things I'd like to understand better about this going forward. I guess briefly, basically there's existing work on kind of studying families of varieties and things, but usually one-dimensional families because we need transcendence degree 1 heights. So using these heights, you can take a lot of those same techniques, but now use these heights that apply in higher transcendence degree and get some results for bigger families there. And then kind of more vague things, I'd like to understand this constructible isotriviality better. And then I think, like I said earlier, these vector valued heights, really all that's happening so far is it's just saying put off the choice of polarization and do it later. But it is a bona fide vector space that we're working with. And I think there's kind of more structure that could be taken advantage of there to really like forget about R-valued heights entirely, or at least put that off for a longer period of time and actually make statements about the vector space structure and get some interesting results out of that. But yeah, thank you. Thank you for the invitation to speak. And it's nice to be able to connect even virtually here. And I'm happy to take any questions.
Any questions?
Can you say a little bit more about the Khrushchevsky's model theory? I never heard of this.
Sure. Let me get back to that. So I won't claim to understand the full detail of their model theory proofs very well. But so one of the things that makes this a little bit difficult to apply directly to this kind of setting is they're really working in fields, and they're setting actually in difference fields, so fields with some automorphism. But in any case, the results are all actually about function fields of varieties, so everything is only up to birational isomorphism. At least in all of their statements about what they even mean by a dynamical system and so on. And then in the positive characteristic case, you have to worry about these kind of inseparable things happening as well. And so their results in some ways are stated in far more generality. So one of the reasons I want to explore these vector valued heights further is they actually make a statement about vector valued heights too. As far as I can tell, it's not really technically related to or I guess yours as well, vector valued heights here. But I think plausibly it could be. And the cool thing that happens in theirs is the requirements they're setting for this is actually far weaker than anything here. So they actually state some results that don't require a polarization, for example. And all of the results, you only need, say, a rational map. You don't need things to extend to an actual morphism as well. So there are a lot of advantages to their work like that. The difficulty is when you do want a morphism translating it. So one of the big problems here is if you have just a rational map, so it's easy just by blowing things up to extend a rational map to a morphism, but that doesn't work for an endomorphism always, because you'll blow up the transform of kind of the top and the bottom versions of this same variety will be different under that blow up. And so I want to explore that geometry a little bit better to kind of understand what's happening there. But it's I think there's a lot of potential for, I'm fairly convinced this is the right approach to isotriviality in this function field case. So I think it's worth understanding better, but I'm far from an expert on that.
Thank you.
Yeah.
Are there more questions? So let us first of all thank the speaker.
Well, thank you.
Thanks, Alex.
So where's the dinner?
Yeah.
For the dinner. Everyone can grab the dinner and we can share.
I will say, Shou, I think via your dining card, which ended up in Xinyi's hands, I think I've had dinner on your tab a couple times while I was in Beijing already.
Oh, okay, yeah.
So maybe got front loaded a year or two, but I'll say thank you long after the fact for that.
Yeah. Also, you were in Beijing.
Yeah, I was there. Let's see, that would have been fall 2018. I was there for a month and a half or so.
I see.
With
What Raphael there?
What was that?
Raphael.
Yes, yeah, he had just started there when I got there. Yeah, is he still there?
Yes.
Okay. Yeah, I haven't been in touch with him recently. I should catch up.
Yeah, he said that in Beijing there's no, now that everybody is you don't need to wear a mask. You can go to dining hall. Everything's open.
Ah, that's nice. Yeah, we haven't been so successful here on that front. Let's see, I'll bring this down.
Yes, it's nice. Yeah, it's quite different, right? I forget what's so this.